Hey everybody, I'm Sam Stosky. I'm the project manager for Primus Locus Engineering. Joined with me today is the team of engineers working alongside me for the County Road 38 project, each assigned to their own discipline as listed. The County Road 38 project is going to be the reconstruction of County Road 38 spanning east to west. There will also be the addition of the new intersection at County Road 21 with a brand new visitor center located here. The visitor center will have clean water supply from the water treatment plant designed by the environmental engineer. There will also be stormwater treatment practices within the project limits to treat for the water quality and flood control volume. So as well as being the project manager, I am also the water resources engineer. Quick design overview for my design. I have bioswales running on the north and south end of the road, passing through culverts and leading to a detention basin located here. At the visitor center, there's a storm sewer system directing the water to an infiltration basin located there. Then on the east side of the bridge, I have a curb and gutter storm sewer system leading to a pretreatment settling pool and then into a rain garden going towards the river. So starting off with the design, with this design, I use Manning's equation. Elkhart County Standards provided a 3-to-1 maximum slope requirement, and for Manning's coefficient, I use a natural straight channel with some grass, which gave a coefficient of 0.026. The west watershed had a peak flow of 3.36 cubic feet per second as calculated last semester. Knowing all these, I was able to find the minimum requirements using Solver and Excel to get this table. I then plugged in the final ditch dimensions of a height of 2 feet, bottom width of 2 feet, and top width of 14 feet. Gave a total peak flow of 95 cubic feet per second, which is much greater than the needed peak flow of 3.36. Moving on, next was culvert design. There were 3 culverts to design within the project, 2 by the visitor center, 1 on the north end and the second on the south end. The third one was right before the bridge leading to the detention basin. Elkhart County Standards provided a 15-inch minimum diameter for the culverts, as well as 6 inches minimum depth below the roadway. Again, I used the 3.36 cubic feet per second for the design flow, and HY8 was the program used for the design. So the first culvert by the visitor center on the north end, it took in 5,200 feet of roadway flow. I used a 1.5 foot diameter concrete culvert and it spanned under 80 feet of roadway width. Cross section here shows the depth below the road as well as the outline of the culvert. The blue line represents the water going into the culvert and the red line is the energy grade line. Second culvert again took in 5,200 feet of roadway flow and I used the same 1.5 foot diameter concrete pipe, and this one spanned under 70 foot of roadway width. And the last culvert took in 2,900 feet of roadway flow, and this one again used the 1.5 feet diameter concrete culvert, and this one spanned under 80 feet of roadway width. Moving on to the detention basin design, at this location, I got a water table of 10 feet. There was the 3-to-1 maximum slope requirements, and I used level pool routing to determine the dimensions. And I used a peak runoff rate of the 3.36 cubic feet per second and a time of concentration of 1.56 hours. With level pool routing, I developed the inflow-outflow hydrograph. The blue line represents the inflow using the rational method, and the orange line represents the outflow with level pool routing. The intersection there of the two represents the peak storage for the pond. After completing level pool routing, I got the ditch dimensions, which will be an 8 feet deep detention basin. The X represents the length, the Y represents the width. And I use an outflow structure of 1/2 foot in diameter, and the peak storage calculated using level pool routing was about 124,000 cubic feet, and my total pond storage can hold 155,000 cubic feet. Next was the infiltration basin design right by the visitor center. Here I had a water table depth of 8 feet. I used the same slope requirements, and there was also a requirement to infiltrate in 48 hours. And at this location, the media was a hydrologic soil group C, which is an infiltration rate of 0.2 inch per hour, and my depth was 5 feet. The total pond would infiltrate in about 25 hours, which would meet the 48-hour requirement. The total volume for this basin was about 115,000 cubic feet. The next design was the grass section design. There was 2 main areas where the grass section would be implemented. That would be within the parking lot, between the parking spaces, and on the outside of the parking lot, leading the flow as pretreatment into the infiltration basin there. So within the parking lot, it'll all be directed towards the proposed storm sewer. There will be 4 strips, and each strip is going to be 165 feet by 2 feet. And then for the west parking lot section, outside of the parking lot, that section will be 325 feet by 150 feet. On the east side, it'll be 400 feet by 175 feet. There was 2 rain gardens to design for this project. The first one was the west rain garden west of the bridge, right before the detention basin. Right before the basin, the water table depth was 8 feet. It used the same slope requirements and the same drainage requirements. The depth here was 4 feet and the infiltration time was 20 hours. This one does have an under drain with an under drain diameter of 1/2 foot. The next rain garden was east of the bridge. This one will have the pre-treatment settling pool, bringing the water into it. This had the same slope requirements, and this one did not have an under drain, and this one will flow right into the river. The inflow pipe from the pre-treatment settling pool was 1/2 foot in diameter. The depth here was 3 feet. Next was the pre-treatment settling pool design. This water collects from the storm sewer and allows the solids to settle, and then when it reaches the depth, it will flow into the rain garden and the pipe. And the depth here was 4 feet, and this holds a total volume of about 5,800 cubic feet. Moving on to the east side of the bridge, I had curb and gutter design. Elkhart County standards provided 400 feet of maximum spacing. This was about a 1,500-foot roadway section on both the north and south end. So I chose to do 5 inlets on each side, which would provide 300-foot spacing. And shown here in the image, the south flow will be directed to the north side of the road, leading to the pre-treatment settling pool here. For the storm sewer design, there's 2 storm sewers to design, one at the visitor center and another on the east side of the bridge. For the one by the visitor center, this was a 6.2 acre watershed. Elkhart County standards said to use the 10-year, 24-hour storm requirement to design this. Gave an intensity of 0.14 inch per hour. The runoff coefficient of 0.95 for the impervious area. Table here shows summarized calculation of the pipe diameter, which was 0.58 feet. So I used a 8-inch pipe, and I used the energy grade line and elevation as a comparison to check and ensure that it was working. Lastly, the storm sewer on the east side of the bridge had 10 total inlets on 5 each side. This was a 2.03 acre watershed. Again, use the same storm requirement with same intensity and same runoff coefficient. Table here shows the calculated pipe diameter summary, and the inflow would accumulate throughout each inlet. And the largest calculated pipe diameter was 0.141 feet. So I used a 4-inch pipe for the storm sewer. And again, I used the EGL and elevation comparison to make sure it worked. Moving on, the construction costs for the water resources. I have each stormwater practice with the relative quantity and relative unit, and the price factor relative to those units. And the total rounded value for that was about $1,040,000. Thank you. I'll now pass the mic to Sim.
Thank you, Sam. I'm Simeon, and I represent the environmental engineering team at PLE. The scope of the environmental work includes providing clean water to the visitor center in the most efficient manner possible. This involves meeting a daily demand on average of 1 million gallons, as well as meeting the EPA's most recent standards. The phase 1 portion of the project included doing an alternative analysis to determine the water source. Water source selected was the Elkhart River, and a river quality assessment was done to determine the contaminants of concern to help guide the design process. The design is broken into 5 components, as shown on the process diagram. Each component is designed with redundancy to ensure that operation and maintenance can occur going forward in the future after the construction. The first portion of design includes the water intake. Several constraints were satisfied, including determining if the extraction rate would satisfy the long-term median flow rate, which it did. Additionally, the intake was separated from the future wastewater discharge point, and consideration for marine life was taken by putting a screen and velocity cap on the intake. Displayed here are some of the results, including the river dimensions and the pump power required to supply the water treatment plant. The second portion of design includes the coagulation and flocculation design. Coagulation consists of higher speed mixing with alum dosage, while flocculation is slower speed mixing. Once again, the calculations were done to determine the dimensions, and those dimensions were implemented onto CAD drawings as shown here. Water flows in through a pipe into the coagulation basin, which is the smaller chamber, before going into 3 larger chambers representing the flocculation basins. The third portion of design is the sedimentation. The alternative analysis yielded a circular geometry for the design due to its higher detention time and greater rates of settling. The dimensions are displayed on the right, and those were implemented into this profile image of the sedimentation basin, where water enters through the influent pipe and moves towards the outside, promoting settling of particles. The fourth portion of design was the rapid sand filtration and disinfection. The rapid sand filtration is driven by gravity and relies on mechanical straining and adsorption to material to remove finer particles from the water. Additionally, a backwash system was implemented, so the collected particles can be removed from the media and removed and disposed of. Chlorination was the selected form of disinfection due to its optimal cost and standardized use in the US as a disinfection practice. Finally, fluoridation was also included to ensure that no tooth decay occurs for water consumers. Displayed here is a plan view of the rapid sand filter with 2 separate cells. Water enters in and settles in the media before leaving in an underdrain pipe. Another profile image shows the water moving down through the media, which includes 3 layers, the top being anthracite, the middle being sand, and the bottom being gravel, each specifically sized. And the valve network displays the backwash system to remove the collected particles. Displayed here are the disinfection results. The residual chlorine concentration was determined to be 1 milligram per liter, and the average temperature of 42 degrees Fahrenheit in Goshen was used to calculate the residual fluorine concentration, which was 1.25 milligrams per liter. Those were used to size the injection feed systems. The final component of design was the water distribution network. The water storage required 2 tanks, each holding 1 million gallons per day. Fire demands were also satisfied by providing a fire hydrant outside of the visitor center that can provide 20 psi and 1,000 gallons per minute of flow for a duration of at least 2 hours. The piping network was constructed with ductile iron pipe, and pump sizing was calculated to transport the water from the treatment location, which is offsite, to the visitor center. So displayed here is the water storage tank. There are 2 of them. Water distribution results indicate the required number of pumps and pump size. And displayed here is the water treatment plant on the bottom right corner, and the pipe network transporting the water through ductile iron pipe to the visitor center. Finally, the construction cost calculation was done using both RS means and the EPA's water treatment cost estimator. Since the EPA's water treatment cost estimator is an older source, the consumer price index was used to determine an inflation rate to apply to that. Additionally, RS means city cost index was applied to each line item. Each line item also received a 10% contingency, and when added together, the final cost came in a little bit under $8,200,000. Thank you. Here's Teo.
My name is Mateo Duran, and I will be representing the structural engineering department at PLE. So I will be going briefly over the design overview, which we have the 41,800 square foot visitor center. In that visitor center, we had to design for the occupational loading. Then from those loadings, we found the gravity loadings that was designed for in RISA floor. And then we had the lateral loadings that were designed for RISA 3D, such as your seismic loadings and your wind loadings. And from there, we designed the concrete elements, the masonry elements, and as well as the timber elements and the connections. So this is kind of the general overview of our structure. Like many visitor centers, it has the masonry exterior. And you can see right here, we have various joists, long span joists being supported by joist girders and columns. On top of this, which is not shown, is our composite decking that was used. On the second floor, we have timber roof joists that are used for aesthetic, because that's going to be kind of like It's designed to be a restaurant area. And then we have steel decking on top of that for the roof. And we also have a covered outdoor space here, which is timber as well, with the steel decking for the roof. So this is the member layout of the entire facility. All in all, 41,800 square feet, with the first floor being 32,800 square feet and the second floor being 9,000 square feet with an additional 1,800 square feet of covered space. This is the general outline. You can sort of see from here where the second floor is going to be supported by these different beams and columns here. This is the distribution of the decking and the area loads. For the decking, we use composite decking to have a more rigid structure and to allow for an easier installation for those concrete slabs. And we have 3 different area loads that were applied on top of that decking as well. Here are the various loadings that we have. We have the restaurant, terrace, and roof garden loading, which are each 100 PSF each. Then we have a snow live load of 44 PSF, a roof dead and live load of 20 and 10 PSF. And then the composite decking load with the floor slab on it for 44 PSF. Here's a closer look at some of the design members that were designed by Riza Floor. As you can see, we have the masonry in red. We have some long span joists with 8-foot spacing, 5-foot spacing. And we also have W sections that are used as columns and also W sections for our beams to resist lateral loading and that gravity loading that we have. Here's a list of the members that we have. Once again, long span joist with joist girders. We have our W-shaped beams and W-shaped columns. And we also have various timber sections which are made with Douglas fir, and that includes the columns and the beams as well. Here's what our 2 designs look like for the floor slabs. Because we have 5-foot spacing and 8-foot spacing, we had to come up with 2 different designs. They both have a depth of 5 inches to have a continuous floor for the second story. And they both include the use of number 3 size rebar in them for reinforcements. And the 8-foot spacing does have to use a number 5 size rebar because it does have a little bit of a longer span there. And this is a typical design for the masonry that we have. Riza 3D designed this, and as you can see, there's a lot of steel reinforcement throughout it to help redistribute that load path to help keep our structure stable. And these were also checked by hand. And then we have the timber roof truss that was designed. This below, there's the typical layout of the roof truss, about a 60-foot span. And above, you can see that they're spaced out at 15 feet, and they also have lateral bracing in between them to help with the lateral loading as well, with that steel deck on top of it. And this is the layout of the covered space that we have. Once again, timber, typical sections where we just have a 30 by 60-foot layout with the steel deck on top of it to make it a covered space. And we have braces across for that lateral loading as well. And then we have our connections, to which we had joist to masonry, girder to masonry, joist girder to column, joist on beam, girder to girder, and then beam to girder. On the right, you can see the typical joist girder on column connection, where we have our typical 1-inch bolt that we use throughout the building, as well as a 1/2-inch thick plate that we use for bearing. And we had to design for shear, bearing, tear out, as well as prying action on those members. And all in all, we have our construction cost estimate that comes out to 15 million. This was done by taking each of the components, their units, and then the unit cost, multiplying that by the quantity that we would need for each of those sections, and then we get a cost. We add contingency to that to round up the cost, and that's how we get to our 15 million. Thank you, and I'm going to pass it over to Vince.
So with the transportation department, my objective was to design an intersection for pedestrians, bikers, and motorists that's safe for them to all be able to cross. I also had to add a center turn lane to County Road 38. Parking must meet ADA standards, and I also plan to have a multi-use path connection to the south of the roadway just for safety. And I also had to make sure that the intersection turn radii was proper for larger vehicles like trucks and everything to cross. I also had to do the underpass profile on the east end of the project limits. So these are some of the details for the roadway. As I mentioned earlier, The WB 67 design vehicle is what I use, which is the Indiana design vehicle. It is a 45 mile/hour speed limit on this roadway. This roadway has a minimum grade of 0.5% with a maximum grade of 5 and a minimum curve radius of 585 feet. And these are some of the criteria, constraints, and assumptions. I assumed a lane width of 12 feet, a paved shoulder width on each side of the road of 10 feet, center turn lane of 12 feet and a ditch for 14 feet and a path of 10.5 feet. All of the dimensions for the roadway came from the NDOT design manual, figures 53, 1, and 2. And this is the typical section for the roadway. You can see I have my multi-use path. That's noted by MP and is 6 inches in thickness. The ditch will also have 4-to-1 slopes, and the mainline pavement, center turn lane, and shoulder will all consist of HMA type B pavement. And for the intersection, I have dedicated left turn lanes going west and eastbound. There's also islands that separate turn movements going through and turning right. There's also pedestrian crossing on the southern portion of the intersection, as mentioned earlier. And these are the details of the intersection. As you can see, I have my path with the pedestrian crossing on the south end and also the different channelized turn islands. And for the visitor center, for the parking lot, we had to do 133 spaces. We determined this number earlier in the semester. Each space is about 11 feet wide and 20 feet long. There's 2 van accessible spaces and 6 handicap parking spaces. And there's also grass strips between each of the aisles as coordinated with the water resources engineer. And there's also at least 24 feet between lot sections in order to allow entering and exiting traffic to safely navigate the parking lot of the visitor center. And this is just an overview of the parking lot. As you can see, we have our sidewalk with our pedestrian crossing at the north. We also have our traffic going through and our grass strips shown in this figure with the accessible parking at the bottom. And this is the southern portion of the parking lot. There's a designated space for larger vehicles like buses and trucks for larger events that may happen at this visitor center. We also have areas for trash collection and a 75-foot turn radius for larger vehicles like trucks to enter the entrance building. And this is just the profile for the bridge and underpass shown at the end of the project limits. And this is my detour plan. As you can see in the black, we have the westbound traffic. In the orange, we have the eastbound, blue, southbound, and green, northbound. And this is all going to be utilized once the road is closed at this intersection for a certain period of time. And this is my cost estimate. As you can see, the traffic signal is one of the more expensive items, costing around $500,000. And there's also things like the roadway signs, parking lot signs, and also like striping, lighting, and concrete for the sidewalk and everything. All of this totals out to be rounded up to about $2.3 million. And I'm going to pass the mic off to Sam to do the cumulative cost estimate for each discipline.
Thanks, Vince. So in addition to all the construction costs, there was also a design cost calculated last semester that had an hourly wage of $35 an hour for each engineer, as well as $40 an hour for the PM. There was an overhead of 155%. So the total cost for design calculated last semester was about $100,000. And then as each engineer just went through their respective discipline and the cost, the total cost comes out to about $26.6 million for the total construction cost. Thank you. Any questions?
So on the water resources and transportation side.
Yeah.
So related to the parking lot, we both talked about that and the grass strips. Can you talk a little bit about like the slope or how that area is graded? And also what criteria do you use for grass strips and things like that?
So for slopes, I guess I don't have specific like slope to say, but I had this like left portion of the lot sloped towards the storm sewer, and then this right portion sloped the opposite way towards the storm sewer. But I personally don't have a slope on the parking lot. Vince, I'm not sure if you have a slope.
I don't have an exact slope.
And then as for the criteria,
Yeah, and like when you size them out, or are you looking for Like what criteria is there, like for your ditch, right, you have certain.
Oh.
Your detention basin.
Like the,
Is there any-
like I didn't have any standards that I saw at least, but I just coordinated with him and got the size of it all with each spacing and then worked in the length for that and then the width. I didn't really have a criteria for that. I just kind of my best engineering decision there.
So two questions up for you, Sam, but I'll ask them kind of both at once. So, does Elkhart have a minimum diameter storm sewer pipe? Because 4 inches seems kind of small.
Small.
And then the detention pond design, it's 8 feet deep. Is there a maximum? Because that seems kind of deep.
It's detention pond. I mean, I guess I'd have to double check, but I'm pretty positive I followed all the, at least the Elkhart regulations. There could be a depth. I didn't see one that I know of, but for the storm sewer pipe, is there one? Is there?
There's not a maximum depth, but there is a minimum.
Okay.
Storm sewer size.
For it, I thought 4 inches probably seemed pretty small too, but I just figured I did the calculations right, so I didn't want to stray away from design, but I could have gone bigger, it wouldn't have hurt, even though I guess I tried to maximize the cost efficiency and keep them smaller, but.
No, Sam, I'm gonna ask you this question. You sort of answered by not looking at the standards, but for the swales,
Yeah.
what would be, I'm remembering like mentioning a flow rate of 95 something in there. It's a huge number in my judgment. And then the first thing comes to mind is the flow velocity in here. And as part of the stormwater management, you do not want to erode that swale you are designing in there given that. So what is, I tried to actually scan through that table you are putting in there, and I did not see, except if you pointed out to me, like what would be the flow velocity given that 95 CFS flow rate?
Right, I guess I don't have the velocity in here, I could. Probably calculate it, it'd probably be pretty big,
Yeah.
could cause issues. I designed that because I knew I had to at least account for the 3.36 and I didn't want to, I wanted to make a, a nice ditch. I could have probably gone a little smaller, but I also had to account for like the slope requirements and things like that, but.
I could tell you the Indiana manual requires that the velocity be somewhere between 2 and 10.
Okay.
So minimum, even though the slower the better, it removes the sediments, but they wanted it still to be above 2 and less than 10 to prevent erosion of that. And also caught my attention, if you do not know the slope of that grass area and the parking lot, how did you come up with the flow rates?
Well, I know the slope of the entire like channel. Like the bioswale, is that what you're asking?
And I'm usually since you use the rational method, you tend to divide your watershed into smaller areas and figure out what will be the flow rates that goes into each, either like rain garden or catch basin and so on. And so that knowing the slope is part of that formula or equation.
Yeah. Like for the storm sewer or for the ditch design? Or,
All of the above.
yeah.
Yeah.
I used the slope here for Manny's equation of the channel, knowing like the elevations and the lengths and things like that. But for the storm sewer design, I also had a slope. Well, I didn't show it in here, but it's in my report. I guess I can't tell you the slope right.
Question for Sam. Sam, what would be the fire demand since you are considering both the visiting center water use and the fire demand? And you designed your system for what, 1 million gallons per day?
Yes, yeah, they were Fire demand was 20 PSI and 1,000 gallons per minute for a duration of 2 hours. I don't remember exactly what the visitor center demand was based on the 40,000 square acres, but I know the water provided was well above. I know my average daily demand, converts to roughly 4,000 gallons per minute. So it exceeds the fire demand, and I knew that the building was less than the 1,000. So I don't remember the exact number of the building, but it satisfies both of them.
My last question, I promise, Theo, what type of lateral loading resistance system I saw the cross bracing across the windows. I thought they are the windows. Are you putting the cross bracing across the windows or somewhere? Can you show it on your graphical?
I'll show you on this. So the lateral design, I have a couple different portions for that. So the main lateral resistance that I have is done through these beams and columns, the W sections, as well as with the masonry, which has the reinforcement in it, and Risa designed that to be adequate for that lateral resistance. And then for the roof on top of the restaurant, this one right here, Risa had a tough time calculating it, but once I threw in these lateral braces here, then they was able to resist for that wind load and the seismic load up at that level as well.
Thank you.
That's my boy. Yeah, for seeing your presentation and that was him answering it. It sounded good. I have no idea what he's talking about, but it sounds good. Right? Oh my gosh.
So about this. This is so much fun. No, Vance. Can you go to your intersection plan view and explain how it works? Yeah.
This one?
Sure.
So pretty much I have the channelized islands like going through the intersection just to separate like turn movement going right. Then I also have like the pedestrian crossing. They're gonna like come down, people like walking from the visitor center, I guess would come down, cross over there, and then the path would go all the way to the end of the site from there. And then I also have like the different turn lanes, of course, which, like for left turns.
So the car is heading west and must turn left. Where does he turn left into? No. Vertical. That's. Where's he go?
Like you kind of go through like between the channelized islands, I guess.
So I'm wondering. You have all these curve radii, but if there's a truck trying to turn left, it's.
It should have enough room. So it was basically required that we needed like 125 feet for the larger trucks, the WB 67. Each of these turn radiuses is 125 feet for that truck to make a turn.
Okay.
Yeah, just a follow-up on that table, that's that 95 CFS flow in the ditch, is that the flow area that's 16 square feet?
Sorry, 1 second. So your question is,
Area 16. Is that the flow area, the cross section of the flow?
yes.
Okay, so the velocity is less than 6 feet per second.
Oh, okay. Yeah, you're right. I guess I could, yeah.
Assuming it's flowing full, correct?
If it's going full, yeah. Anybody else? Thank you.
At this point.